Calculus is one of the most profound intellectual achievements of humankind. It deals with continuous change, allowing us to analyze motion, change, and growth. Before calculus, mathematicians struggled to describe accelerating objects. Calculus provided tools to calculate instantaneous rates of change. This breakthrough opened new avenues in physics, astronomy, and engineering. The invention of calculus was the culmination of centuries of mathematical thought. Ancient Greek mathematicians, like Archimedes, developed methods for finding areas and volumes. These methods foreshadowed key ideas of calculus. However, it was not until the 17th century that calculus emerged as a distinct branch. Contributions from many brilliant minds led to its development. Two central ideas lie at the heart of calculus: limits and infinitesimals. Imagine approaching a wall, each step halving the distance. You get close but never touch it. This idea is crucial to understanding instantaneous rates of change. Infinitesimals are infinitely small quantities, smaller than any measurable number, yet not zero. Calculus embraced them, unlocking the secrets of continuous change. This paved the way for the groundbreaking work of Newton and Leibniz. Isaac Newton, the English physicist and mathematician, is one of the most influential scientists of all time. Newton's development of calculus, which he called fluxions, was deeply intertwined with his work in physics. He imagined quantities as continuously flowing and developed methods to calculate their rates of change. Across the English Channel, German mathematician Gottfried Wilhelm Leibniz developed his own version of calculus. He introduced the integral sign and the concept of differentials, using dx and di to represent infinitesimal changes. His notation is still widely used today. This fueled a controversy over the invention of calculus. The stage was set for a clash of titans. In the late 17th century, the rivalry between Newton and Leibniz over the invention of calculus erupted into a full-blown controversy. The dispute, fueled by nationalistic tensions and professional rivalry, cast a long shadow over the mathematical community. At the heart of the controversy was the question of priority. Newton claimed to have developed his method of fluxions in the 1660s, but published later. Leibniz published his version in the 1680s, making him the first to publicly disseminate his findings. The differences in their notations and approaches fueled the debate over originality and ownership. The Newton-Leibniz controversy quickly escalated beyond a mere academic debate. It became entangled with national pride and political tensions between England and the European continent. English mathematicians, eager to claim the glory for their nation, rallied behind Newton, accusing Leibniz of plagiarism. On the continent, mathematicians largely sided with Leibniz, pointing to his earlier publication date and elegant notation. The dispute became a battle for national scientific supremacy, with each side fiercely defending their champion. The controversy created a rift between the English and continental mathematical communities, hindering communication and collaboration. It cast a long shadow over the legacy of both Newton and Leibniz. In 1711, the Royal Society, England's prestigious scientific institution, appointed a committee to investigate the priority dispute. The committee, heavily stacked with Newton's supporters, delivered a predictably biased report in 1712. They declared Newton the true inventor of calculus and accused Leibniz of plagiarism. The Royal Society's verdict did little to quell the controversy. Critics accused the committee of bias, pointing out Newton's influence on their findings. The report deepened the divide between English and continental mathematicians. This intellectual isolation hindered the progress of mathematics on both sides of the English Channel. It would take decades for the mathematical community to overcome the divisions sown by this bitter dispute. The Newton-Leibniz controversy had a profound and lasting impact on the mathematical community. It created a rift between English and continental mathematicians, hindering the exchange of ideas and collaboration for decades. English mathematicians, largely adhering to Newton's notation and methods, developed a distinct mathematical tradition. On the continent, Leibniz's notation and approach to calculus prevailed. This divergence created a significant barrier to communication and collaboration. The rivalry cast a long shadow over the legacies of both Newton and Leibniz. The controversy serves as a cautionary tale about the dangers of nationalistic rivalries and the importance of open communication. Despite the bitter rivalry, the genius of both Newton and Leibniz eventually shone through. The power and utility of calculus, regardless of its originator, were undeniable. Mathematicians and scientists gradually recognized the contributions of both men. Leibniz's notation, with its intuitive symbols and rules, became the standard for calculus. Newton's work on physics had a profound impact on classical physics. Over time, the controversy faded into history. Mathematicians came to appreciate the unique contributions of both Newton and Leibniz. Calculus was the culmination of centuries of mathematical thought, reaching its zenith in these two giants. The legacy of calculus extends far beyond the controversy surrounding its invention. Calculus stands as one of the greatest intellectual achievements of humankind. It provided a powerful new language to describe change and motion. Calculus revolutionized mathematics and science, unlocking new frontiers in fields ranging from physics to economics. Newton's calculus laid the foundation for classical physics. Leibniz's calculus proved incredibly versatile, finding applications in geometry, probability, and engineering. Today, calculus is an indispensable tool in countless fields, shaping our understanding of the universe. Its impact on our world is immeasurable, continuing to solve complex problems.